Alright, this is Physics Lab 2, where I'll be observing a yellow ball falling to the ground after being dropped from rest. And we're going to analyze this video in Tracker to make two model predictions, one with drag and one without drag. And to summarize, I found that the model with drag predicts the motion of the ball a lot better, but we'll see how this works in a little bit. So here's my video. I had to invert the axes a little bit because my camera was a little off, but we can definitely see that the velocity of the ball is increasing. So we have all our points here. So here are the concepts that we'll be using for this lab. Net force isn't zero anymore. We have two forces acting on it, which is the force of gravity, or W, equals negative the mass of the ball times force of gravity times J hat, and the drag force, which is negative B times the magnitude of the velocity squared. And then the net force will be the sum of these two forces. We'll also be using Newton's second principle in this lab to predict the final velocity of the ball after each time interval, and this will be used to predict the position also. So here are initial conditions. Here's the mass of the ball in kilograms. The position and the velocity vector are both 0, 0, 0. B I found was 0.00607. And then here is our code. Here's the equation for the gravity force, and for our first run of code, we're just seeing how the ball moves with only gravity as the force acting on it. So F net is just equal to W here, and the drag force is commented out. So let's see how that looks. As you can see, there's only a yellow arrow pointing down for gravity. And then here, let's uncomment our lines of code, add in the drag force, and then let's run it again. So now there's a second arrow acting on the ball, the blue arrow pointing up, which is the drag force. And then the final position is negative 1.767, which is equal to the final experimental position, and that's how I found B. Alright, so let's analyze the graphs that we found. The one on the right, or here, let's do this. The one on the left is my model without drag. As you can see, the red line's the model. As you can see, it over predicts my position by not too much, but you can see that the difference is increasing. So as time goes on, the error will continue to be greater. But we see here that my model with drag force predicts it a lot better. The initial points lie on the red line directly. We see a little bit of deviation here, but then we return, the points return to the line at the end of the time interval. And this deviation could be caused by me not putting the points in correctly, because the ball was a little blurry at times. Another thing is I filmed this inside, so the camera frame rate might be off. But overall, we can see that the slopes are very similar. The graphs, the points, even though they don't really, not all of them lie directly on the line, they are definitely very close to the line. So what does this mean when we're discussing velocity versus time and terminal velocity? Here is the graph of the blue line is the velocity without drag, and the red line is the velocity with drag. As we can see here, the velocity with drag model has a terminal velocity, whereas if we didn't have the drag force, the ball would just be falling forever. You know, because the slope is constant, so velocity is constant. So we needed this opposing force acting on the ball. So what happens when we, instead of dropping the ball from rest, we throw the ball down? Well, the terminal velocity will stay the same. The difference would be that the red line would start, maybe down here at negative 0.002 meters per second instead of at 0 because it's not at rest. But the graph would slope downward and eventually meet at the same terminal velocity. So that's it for Lab 2.